In this section, we have a very important theorem called Green's theorem. Now, there are going to be two forms of Green's theorem that correspond to the two forms of the line integral we saw. There's a circulation Green's theorem and a flux Green's theorem. Now, we're going to look at the circulation one first. So we have a vector field f, which is f comma g, and R is some region in 2 space. 2 space, of course, being the real numbers squared. Right, the normal x and y axis that you think of. And it's bounded by a closed curve C. Okay, and we are always going to assume counterclockwise motion. That's just how it is set up. Okay, if that's the case, then the circulation is equal to, and this symbol here on your integral lets you know that the curve C is a closed curve. By putting the circle inside the inner, on top of the integral sign like that, it lets you know that this is closed. So that's what that means when you see that on the integral. All right, so you're going to take the integral of f times t, t being the tangent vector, ds over the arc length, and that's equal to the double integral of the partial derivative of g with respect to x minus the partial derivative of f with respect to y, which I wrote here, gx minus fy. I think that's just easier way to write it. And it's a double integral because you're going to be integrating over the region because it's a closed region, which we have not always had up to this point. Okay, so I drew a picture here. So we have this closed curve C. The region is the interior piece. And your circulation along your boundary is going to depend on something in the inside called the curl. So the curl, the two-dimensional curl, I'll put that right here, curl, in the interior. The curl is the quantity g sub x minus f sub y, right? So g sub x minus fy is the curl. We're going to discuss curl further in the next section, but for right now, that's all you need to know about it. All right, so sometimes you'll see Green's theorem written this way. So, matter of fact, it's often written this way. The curl of f, and everybody assumes you know what curl is, that curl is equal to this. Okay. Now, notice what would happen if the curl was equal to 0, right? So if your curl equals 0, so let me think about this. 1, the curl of f would be 0 because this is the curl, right? So that would make it 0, which that would mean that the circulation is 0 on that curve. Because if the curl is 0, you're integrating 0. Right? If this is 0 in here, then when you integrate it, you get 0. So it would be 0. And what would that mean? Well, let's look at this another way. So this is g sub x minus f sub y would be 0. So if I add f sub y to both sides, that would mean g sub x equals f sub y. And that should look familiar to us because we've seen that already. That's our definition for what it meant for f to be a conservative vector field. Another word for conservative, by the way, I gave you other ones for source-free, irrotational. Irrotational. There we go. Always takes me a second to write that one. Chanel. That's an N. Right, they mean the same thing. So irrotational vector field is also a conservative vector field. All right, so let's find the circulation for f equals negative 3y comma 3x, and c is the path shown right here. We're going to do this problem using two different methods. We're going to do direct evaluation. All right, so we've called that something else. We've called it parameterization. It's the original method we first learned in this chapter. And then we're going to try Green's theorem. Okay, so if we're going to do parameterization, we are in a bit of a pickle because we don't just have one curve. We have 3 separate curves. So we're actually going to have to do 3 separate integrals for this, believe it or not. So we have y equals 0 down here, we have x equals 0 over here, and we have y equals 1 minus x over here on the diagonal line. All right, we're going to call this A, side A, this side B, and this side C. And we're going to have to find parameterizations for all three parts. Oh my goodness. Okay, so let's do A right here. Let's see if we can fit them all in side by side. So if A is x equals 0, then r of t would be equal to 0t. Remember that the vertical lines always work a little differently. And then t would be going from, oh, and remember, sorry, I should have put that on there. We're always assuming a counterclockwise orientation. So we're going this way. So we're going from t equals 1 to t equals 0. All right. And then we can find r prime. R prime of t would be 0, 1. And then our vector field is going to be, it was negative 3y, 3x. But remember, this is now my x and my y that I have for my r. So it's going to be negative 3t, 0. Okay, so we'll find that piece in a second. Then we need to, oh, well, I guess I can write the integral. So we're going to find the integral from 1 to 0 of negative 3t comma 0 dot product with 0, 1 dt, which is a big whole whopping 0 because we're integrating 0 and that's 0. All right, well, that one was easy. Let's try the next one. Okay, so part B would be y equals 0. Okay, in this case, r of t is equal to t comma 0, where t is going from 0 to 1. R prime of t is 1 comma 0, and then f would be negative 3 times 0, which is 0, and then 3t. So 3x becomes 3t. So then we're integrating from 0 to 1 of 0 comma 3t dot product with 1 comma 0. And yet again, we are integrating from 0 to 1 of 0 dt, which is 0. All right, so far we're a bust. We're finding zeros everywhere. The last one is not 0, I can tell you that. Okay, so part C, y equals 1 minus x. Okay, so the way to write that, r of t is equal to t 1 minus t. T is going from over here at 1 back to 0, right? Because we have to do that orientation. So t is going from 1 to 0. All right, then r prime is 1, negative 1. F is negative 3 times y. So that's negative 3 times 1 minus t, and then 3 times x, which is 3t. Which I would rewrite that as negative 3t, or excuse me, 3t minus 3, because I would distribute. Negative 3 times negative t is 3t minus 3. 3t. There we go. All right, so we're going to integrate from 1 to 0, 3t minus 3, comma 3t, dot product with 1, negative 1, dt. All right, so this would be 3t minus 3, so the integral from 1 to 0, 3t minus 3 minus 3t dt, which that all goes away. So we're integrating negative 3, which is negative 3t from 1 to 0, which would be 0 take away negative 3, which is 3. All right, putting these all together, it just worked out for us that 3 of them, or 2 of them were 0. So the circulation is 0 plus 0 plus 3, which is 3. That's the parameterization method, right? We would have to parameterize each curve on its own. All right, so let's use Green's theorem. And I'll do it in green, all appropriate. So this was method 1. I should have actually mentioned that. So method 1, which is called direct evaluation or parameterization. Is what we just did. The long, slogging road. All right, so now let's do Green's theorem. Okay, so Green's theorem, method 2. Is that the circulation is equal to the circuit integral, if you will, right, the line integral along the circuit, along the closed path ds, which is equal to the double integral over the region of g sub x minus f sub y dA. All right, luckily for us, we know how to do double integrals. So we need to rethink our integration space. We do know we can find g sub x and f sub y. So to find these, you have to remember that the original vector field is given to you as fg. That's f and that's g. So the derivative of g with respect to x is 3, and the derivative of f with respect to y is negative 3. So it's going to be 3 take away negative 3. All right, now we need to do dA. So we can either go dy dx or we can go dx dy. This sounds familiar, right? So if we go back and we think about the region inside the triangle now, right? Rather than thinking about the outer edges like we were before for the previous portion when we were parameterizing, let's think about this region, R, right? The inner portion is the region. Okay, so now we have to decide, are we going to have approximating rectangles that are vertical or horizontal? In general, if you have a choice, you go with vertical because you're more comfortable with that because of your years of algebra class, right? And we already know the top is at y equals 1 minus x. Okay, so we're going to say dy dx. Y starts at the bottom and goes up to that diagonal line. So it's going from 0 to 1 minus x. X is going from the left side of the triangle, which was at 0, to the right side of the triangle, which is 1. Right? The last integral always has to have constants. Okay, so this is really 6. So integrating that, that would be 6y from 0 to 1 minus x, and then we have an integral from 0 to 1 outside of that. Okay, so this will become 6 times 1 minus x, or 6, if you will, it's 6 integral 0 to 1, 1 minus x dx. And the integral of 1 minus x would be 6 times x minus 1/2 x squared from 0 to 1. So that becomes 6 times 1 minus 1/2, or 6 times 1/2, which is 3. Same answer, but a different method. And it's a much easier method, right? This was much simpler to set up as a double integral and just do this, rather than finding 3 different parameterized functions, integrating all 3 separate functions and then adding them up. So hooray for Green's theorem. If we have a closed circuit, Green's theorem is great to use.